Hey, AP Chemsters, this is Mrs. Vanderlei bringing you the 8.3 edition of Blank Wall. We are starting off in Chapter 8 where Chapter 7 left off. If you remember, Chapter 7 we talked about the quantum mechanics, and what do we talk about quantum? Quantum means a definite amount of energy, and we're talking all Chapter 7 in terms of electrons. And I had told you that we really care about this because we really want to know where these electrons are so we can look at them for bonding. So this is an extension of what we were doing in Chapter 7. We pick up where Schrodinger left off. Schrodinger, if you remember, came up with the fancy equation to tell you where are the most probable locations of electrons. And he came up with the S, which was the sphere, and the P, which was the peanut, and the D, which was daisy, and the F, which was flowers. And he came up with those shapes to describe where the likelihood to find the electrons. And we went through that whole thing. We have 1 S, we have 3 Ps, 5 Ds, 7 Fs, and a possible, once we get to element 121, 9 Gs. So what do we do with that? If I were you, I would try to find a periodic table, maybe one that you can write on. You should have a lot of different periodic tables perhaps. If not, I can always give you another one. And we're going to be looking at, so have a periodic table very, very handy. Look like you're looking right at it as we go through this section. So if you need to pause this to find a periodic table, please do so. Okay, hopefully you found your periodic table, and we started off in section 8.3 about electron configurations. This is how electrons occupy their orbitals, okay? So if I were to look at a periodic table, here's one I picked up from the internet here, and I liked this one because it has a certain feature which I was very interested in, and that has to do with these numbers here. 1, 2, these are your energy orbitals, okay? And remember what we had said with chapter 7 is that when element 119 comes, we're going to have to add a whole nother electron energy, if you will, energy shell to our periodic table that will start your energy level of 8. So that comes into this electron configuration. So electron configuration is like an address. How do I describe where the electrons go? So these are my energy shells, 1, 2, 3, 4, 5, 6, 7. These are my orbitals. This is where the S is. This is where the P is, if you remember. All right, this is where the D is, and let me scooch it down, and this is where our F's are. And one day we'll have a whole new section where the G's will be, but we're not there yet, okay? And so the electron configuration deals with what energy level you're at, 1, 2, 3, 4, 5, 6, 7, what subshell you're at, S, P, T, or F, and then how many electrons are in that particular spot. Maybe this brings back fond memories of when you had first year chemistry when we did this kind of thing. So let's kind of go back here again. So electron configuration is how electrons occupy their orbitals. So the electron configuration is a way to show the exact location of each electron. We're talking about right now its ground state. Do you remember before I ate my chocolate, I was on the ground state, the most stable configuration. All right, I am not excited, okay, to go to a higher energy level. So it's the lowest possible energy of a particular electron, the one that is not excited. So for example, let's look at hydrogen. We call 1s1. And what does this 1 mean? That 1 is your energy level, or the energy shell. All right, level. Okay, the S stands for, right there, the sublevel or the orbital. S, P, D, or F. And then if you have this 1, let me circle that, that means how many electrons. Okay, and there are some rules that we can talk about as far as how to do this electron configuration. The first one is the electron spin and the Pauli exclusion principle. So we can look at this electron configuration and do the orbital notation. It's like a picture representation of what this electron configuration is. And so if I have one electron, see right up here, there's a 1 here, and if you look at the your periodic table, here is the energy level 1. Okay, here's energy level 1. Here is the s orbital. I'm doing hydrogen right here. Here's your s, and then I'm in the first spot. Actually, helium would be right here to be 1s2. But if I'm talking about hydrogen, it's in the 1 energy level, S sublevel, and then it has only 1 electron in the S. If you notice, S can only max out at 2. Okay, so when I do the orbital notation for this, all right, here is my 1s, and then I show the arrow going up, and that tells you I have 1 electron in that shell. But when I showed you helium, look at your helium, there are 2 electrons. So if I were to do helium with 1s2, so how do I do this? I have 1 arrow going up and 1 arrow going down. And those arrows represent spins, all right? And if you recall, we talked about electromagnetic radiation, that if you have a coil of a wire and I put electricity through it, that spinning electrons, if you will cause an electromagnetic or a magnetic field. So we call that, I think, the right-hand rule. So if your coil of wire is going in the way your 4 fingers are of your right hand, your thumb is where the magnetic field is. And so these spinning electrons are creating magnetic fields. So if I have a spinning electron going in, let's say, the north direction here, okay, let's just call that arbitrarily north, all right, I need to have an opposite spin for that magnetic field to coexist, okay? You can't have 2 electrons in the same orbital spinning the exact same direction or they'll repel from each other. So we can max out at 2 electrons, and that's what Pauli exclusion principle tells you. You can only have 2 electrons per orbital, and they have to go in opposite spins, okay? And that's what I'm saying down here. So 2 electrons occupying the same orbital must have opposite spins. And this ties in with Coulomb's law, and we're going to revisit Coulomb's law later on, but understand this is a very important concept in this part of the unit, if you will. It says the potential energy of 2 charged particles depends on their charges, Q1 and Q2, and on their separation of R. R is your radius, okay? R equals radius. How far apart are they? Okay, so if I'm talking about 2 charged particles, so if they're spinning in its opposite directions, one would have, let's say, a charge of a plus, and the other one has a charge of a minus, okay? And so what does this mean to you? So that energy and charge are what? Directly related. As one goes up, the other one goes up. So if I have, let's say, an atom with a charge of +2 or something, all right, that'd be an ion, wouldn't it? And that would have, that +2 would mean it would have more energy. What else does it mean? If I have a positive charge and a negative charge, energy overall is going to be negative. And what does that mean to you? Oh yeah, it's exothermic, remember that? What else this tells me? That energy and radius, all right, are indirectly related, okay? And what does that mean? If radius is small, if radius is low, all right, the energy is high. So if these are close together, it takes a lot of energy to separate them, if you will. All right, if it's really far apart, then there's a lot lower energy. It doesn't take much to pluck them out, if you will. And that will have something to do with down the road when we talk about these atomic trends. All right, so here's our consequences. Like charges, if I have 2 positive or 2 negatives, energy is positive and decreases as the particles get further apart. If I have opposite charges, the energy is negative, becomes more negative, the particles get closer, and and magnitude increases as the charges of the particles increase, all right? So it says, which compound would have a higher potential energy, cesium iodide or lithium fluoride? If you look at your periodic table, what's the charge of cesium? +1. Iodide is -1, lithium's +1, and fluoride is -1. So the charges don't help me. So look at their radii. Cesium is a huge atom. Iodine is a huge atom, okay? So the distance apart is very large. R is large. Lithium fluoride, they're much smaller atoms, so your R is going to be much smaller, so the energy is going to be greater. So this is going to be your answer. Now, if I look at sodium fluoride and magnesium fluoride, the size of the atoms are about the same. If you look at the periodic table, you're talking about sodium and magnesium just one away from each other. If anything, magnesium is a tad smaller than sodium, but not enough to make a whole lot of difference, okay? So what's the difference here? We have a +1 and a -1. We have a +2 and a -1. So the charge is greater with magnesium, so therefore it has a higher potential energy. We're going to talk about this, excuse me, more when we talk about lattice energy later on, okay? So this topic isn't over with yet. We're going to come back to it. So let's go to the next page. Something else to think about as we start putting electrons in, there's something called shielding, which is the repulsion of one electron by other electrons as screen or shielding. So when we have these electrons being put into different energy levels, they're being put in a sense, different shells, okay? So here I have two interior electrons. You see them? They're two interior, and here is another one. So this could be, let's say, lithium. I have the two electrons in the 1s shell, and here's another electron. What this is saying is that this electron here is being shielded from the nucleus, all right? And it's a +3 there. Again, I know it's a lithium there. So these two electrons inside are shielding or repelling, if you will, the electron in the 2s. Because the electrons have like charges, they will repel each other. So this electron is more loosely held, if you will, bound by the nucleus than the interior electrons on. They're shielding each other. So you can call them, they're either shielded or they are repelled. So if this electron can somehow get into the interior, and that's what this means here, then that electron will experience a full +3 charge. It's not being blocked out by the other two, okay? So it says here, figure 8.2, an electron far from the nucleus is partially shielded by the electrons in the 1s orbital, reducing the effective net nuclear charge. We're going to talk about that later, that it experiences. An electron that penetrates the electron cloud of the 1s orbital experiences more of that nuclear charge, okay? And then finally, to start putting this all together, this is actually part of what's called the Aufbau principle, is that if you notice, and this is all part of what Schrodinger did for us, general energy ordering of orbitals for multi-electron atoms. Why did Schrodinger have to even come up with this thing? If you remember, he came about after the Bohr model did, and Bohr only worked for the hydrogen atom. So when you have other atoms with more and more electrons, this is the energy ordering, if you will. 1s is the lowest energy possible, then 2s, then 2p, then 3s, and 3p. And look how muddy it's starting to get here. So here's 4s, but what is a lower energy level than 4s? Over here it's 3d. What's lower after 3d? It's 4p. What's after 4p? It's 5s. What's after 5s? It's 4d comes next, and it goes on and on and on. So we can look at our periodic table that we saw here, and we can order this. This is perfectly aligned as to what Schrodinger said, that here is my 1s, here is my 2s, 2p. I'm filling it in the lowest order. 3s, 3d, 4s. And what is this section right here? It is not 4d, it's 3d. Why is that 3d? Go back over here again and take a look. All right, after 4s, what's my next lower energy? It is 3d. Then what? Oops, sorry, went the wrong way here. Then what? We have 4p, 5s, 4d. Let's see how we can do this. 5p, 6s. But careful. Look at, there's a gap here. Do you see this? This is number 56. Here's number 57. What follows 57 is your 4F. I know that ladder from like 2 pages in front of this doesn't continue on, but notice that the F starts off in the 4. And then this is 5D, 6P, 7S, excuse me, 5F, 6D, 7p. So once we hit here, what will this be? You got it, 8s. And what's going to follow that one day? Oh, what a glorious day that will be. So when we start our new one, it's going to be, guess what? 5g. All right, isn't that cool? That's going to be so cool. Then you'll have your 5g, sorry, then it'll be, what would be after that? 6F, 7D, 8P, and we can keep going and going. And that's what Schrodinger has predicted for us. Isn't that cool? I think that's really pretty awesome. How did I know this was 5G, by the way? Let me show you something. So what does S start with? 1. Okay, and I only get 1. How about 2? I have 2S and 2P. What about 3? What does 3 have? 3S, 3P, 3D. What does 4 have? 4S, 4P, 4D, 4F. So about 5. 5S, 5P, 5D, 5F. And guess what? Once element 121 hits, it's going to be 5G. Isn't that cool? So take a wild stab. And one day, I don't think I'm going to be old enough to see this. You know what? I don't even think you're going to be old enough to see this, but perhaps one day, maybe I'm mistaken, it won't take me forever to, for this to happen. We'll have 6S, 6P, 6D, 6F, 6G, and what will that next orbital start with? 6H. Yes. Okay. Isn't that cool? So do you notice a pattern here? Remember, Schrodinger's answers was very, very, say, geometric, okay? Very, very numerically. So you only have one S. You have 2 different orbitals in the 2 energy level. You got 3 here, you have 4 here, you have 5 here, and that's what the energy level starts with. That's pretty darn cool. All right, I love it. So let's kind of go back here again. So we looked down and we kind of saw the patterns being established here as well. Okay, so what does this tell me one more time? Once we fill the 1S shell, so 1S is filled, then we go to 2S, we'll fill that. Do you remember how we fill the P's? Each one gets its own orbital first, and then we come down and fill these guys up. And here's my 3S, and do the same thing, fill up these first before you come back down and fill up those. Okay, I think we're ready to start practicing. How about you? So here, hang on a second. So I've already alluded to a lot of these rules again. This ladder that we just saw is called the Aufbau, which is a German word, means to build up. Starts with the lowest energy level and you fill it upward, so you can't just start at 2S and ignore your 1S. Hund's rule is when filling the orbitals, electrons fill each orbital of the same energy first with parallel spins, then goes back and fills them with opposite spins. That's what I was talking, let's say, with the 2p. Here's my 2p, right? Oops, I'll write 2p. Excuse me, I fill each one up first, and then I go back down and I fill them going in the opposite spin. So when I go through something like 2p and 3d, I'm doing the Hund's rule. And then summary, the S only has 1 orbital and can hold 2 electrons. The P can have 3 orbitals. And it can have a total of 6 because I can put 2 in each of these. The D has 5, 1, 2, 3, 4, 5, and it can hold 10 electrons. F has 7, can hold 14. So go back and look at your periodic table. So what did we say that S could hold? 1, 2. That's right. What did we say P can hold? 1, 2, 3, 4, 5, 6. That's right. How many did we say D can hold? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. That's right. And what about F? Well, the way this periodic table is shown, we'd start here 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So it starts after that line there. So yes, that makes sense. So what Schrodinger does makes perfect sense with how Mendeleev actually put together this periodic table. All right, so finally there's one more thing to talk about, and that's called the noble gas configuration. You're going to put the previous noble gas in parentheses and then continue on. So let's look at sodium, okay? How many protons does sodium have? What's the atomic number of sodium? It's 11, so I need to put in 11 electrons. So are you looking at your periodic table? I hope so. So let's start. We start from the beginning. I have 1s2, right? Because S can only hold 2. And then start with lithium beryllium. That's your 2s2. All right, so now we're on to boron. Boron is 2p. Now count all the way over. Boron, right, then carbon, then nitrogen, oxygen, fluorine, neon. How many of those can you put in there? You can put in 6. Now if you count, what is 2 plus 2 plus 6, that's 10. I got to go one more, so I go to 3s1. Okay, so how do I do the noble gas configuration? Let's look at your periodic table. All right, so here's sodium. Go backwards. Which is your closest noble gas behind number 11? Well, in this case, it's neon, number 10. So all you have to do is put neon in brackets, all right, and then pick up where neon left off, okay? So how does that work for? So we put neon in brackets. That tells me 1s2, 2s2, 2p6, and then pick up where it left off. So this here is your neon. So where did neon leave off? 3s1. And there you go. You're ready. Okay, that's all there is to it. So let's try some of these. I'll do some of these, and I'd like you to do some of these. How's that? So it says give the electron configuration and the noble gas configuration for the following. Well, how many total electrons does nitrogen have? Well, look at your periodic table. How many does it have? I think it has 7. So where do we begin? We start at the beginning. 1s2. Now what? 2s2. And now count over. Boron is 1, carbon is 2, nitrogen is 3, so it's 2p3. Okay, what's the noble gas configuration? We'll go backwards. Which noble gas comes before nitrogen? And it is helium. So you put that in brackets and then go 2s2, 2p3. Okay, now find vanadium on your periodic table. Now, it's probably no surprise to you why I picked vanadium. After all, it's my favorite element, named after the Norse goddess of beauty. And there it is. So we need to go find, go backwards and start from the beginning. Start with your 1s2, 2s2, 2p6, 3s2, 3p6, 4s2. Now be careful, what does scandium start with? Not 4d, it is 3. That's correct. 3d1, 3d2, 3d3. So let's go back and write that down. Okay, so we have 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d3. So go back to your noble gas, and that would take care of this. This is argon, I believe. All right, so argon goes in parentheses. Now we have 4s2, 3d3. Why don't you take a minute out, and why don't you do lead on your own? Pause this. Okay, how did you do? This is what I got. 1s2. 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, I'm not there yet, 5s2, 4d10, 5p6, 6s2, row, come back down here. Let me scroll up a little bit. That is 4F14. Then this is 5D10, 6P1, 6P2. Okay, so I didn't write it all out on the same piece of paper, but you see how I did that. Make sure you get them all in there. What else can you do to make sure that you did it correctly, or at least a helpful hint? Add up all your subscripts too. So if you have a 2, 2, 6, 2, 6, 2, 10, 6, 2, 10, 6, 2, 14, 10, 2, hopefully it adds up to 82. All right, and that's a good way to also check your work. As far as a noble gas configuration, go backwards, that is xenon. So put xenon in parentheses, then you have your 6s2, 4f14, 5d10, 6p2. So that's how you do lead. So let's see what's next. All right, so why don't you go ahead and do problem number 1. It'll probably take you a while, so why don't you pause this and then see how you do. Okay, I'll just have the answers up here waiting for you when you are done. Okay, pause this. Okay, so here are my answers. I have oxygen, magnesium, aluminum. Notice a couple things. With all your S's, I only drew 1 orbital. With this S, I only drew 1 orbital. But with my P's, I drew 3 orbitals. Remember how many different P shapes are there? There's 3. And then magnesium, aluminum. Sorry, once I started with silicon, I was not going to have enough room for all the arrows. You should have been able to write just fine and get them all in there. Please do not shortcut unless I give you permission to. You should have written out all those arrows. I just didn't have the room, and you could still read it. Hopefully you have no problems with the noble gas configuration. And we got down to chlorine, there you go, and here is scandium. Notice I started my 3D with scandium. So how many things I have? 1 orbital for the S's, but notice I have 5 for the D's, and that can fill up all the way to 10. And the same thing, the bromine, I have 1 S orbital. I actually have 5 of these here, and then 3 of the P's. Okay, hopefully you can read that all right, and hopefully things went well for you. This is a review. I don't think I taught you anything new this time, so that's great. We're done. Oh, I was going to say, don't wait to be great. Bye-bye.